All right, so in this video, we're just going to go through a quick example of using the definition of connectedness to show that intervals in the real line are actually connected, which is what you might have expected. And I realize I forgot to mention that because we defined what it means to be disconnected. So of course, you might have guessed this, but the definition of connectedness, right, is so E is connected if it is not disconnected, right? So let's show, oops. AB is connected for, B greater than A. So say, for contradiction, we can write AB equals AB intersect U1 union AB intersect U2, right? So suppose U1 and U2 are open sets satisfying the definition of disconnectedness for AB, right? So there are other properties, of course, but this is one of them. Okay, so U1 and U2 are open sets. So, okay, the idea is we want to find a place where U1 and U2 end up having to sort of touch each other, basically. So I want to remind you actually of a little thing we did in the proof of the intermediate value theorem, right? Remember how we basically said that the sets where the value of f is less than some y and the set where the value of f is greater than y, they basically have to touch each other at some point, right? Remember that? This logic is actually identical to that, and there's a good reason for that, because we're going to use the concept of connectedness to prove a generalized version of the intermediate value theorem, which I think is actually interesting. But if you remember the trick there, right, to finding the place where the two sets had to be right next to each other, the trick was using the supremum, right? So so set T to be the supremum of AB intersect U1. Okay. And the reason they use an open endpoint here instead of a closed one is because otherwise, it could actually be that U1 actually contains both A and B, and then U2 is in between, is in the middle somewhere. And that's just annoying, because then the supremum actually won't be the place where they touch. It'll just be some random point in the middle, which you could describe some other way. But yeah, anyway, so we're not going to take the supremum of the full intersection, but we're going to take the this supremum here. Okay, so then since a plus epsilon is a subset of U1 for some, and we're assuming A is in U1 without loss of generality. Okay. Okay. Oh, they actually assume that B is in and B is in U2. Okay, so I think actually I'm pretty sure that this endpoint, I think this endpoint could actually be closed. I think it doesn't matter. Well, whatever. Anyway, okay. So actually, yeah, so they're assuming A is in U1 and B is in U2. And this we can do without loss of generality. The reason we can do this without loss of generality is just because if this weren't the case, then actually we could find a smaller closed interval inside of this closed interval where that was true, and then we would just find the contradiction for that one. So yeah. Anyway, so since some neighborhood of A has to be like A is interior to U1, right? So for some epsilon greater than 0, this is true. We have T is greater than A, and since B minus epsilon B is a subset of U2, for some epsilon greater than 0, we have T is less than B strictly, right? Okay, so then if T is in U1, then T minus epsilon, T plus epsilon is a subset of U1 intersect AB for some epsilon greater than 0, right? We can find epsilon small enough so that, right, because T is interior to U1. So clearly some value of epsilon has to make this interval a subset of U1. But then by making epsilon really even smaller than that, we can also force this interval to be a subset of AB, right? So we can find some epsilon such that this is a subset of the intersection here. But then, right, T plus epsilon over 2 is in U1 intersect AB. Oops. Contradicting the definition of T, right? But clearly, right, if T is in, right, so, okay. So then, on the other hand, right, okay. Hopefully you can kind of see how this argument is supposed to go. So let me go back over this. If T is in U2, there exists an epsilon greater than 0 such that T minus epsilon, T plus epsilon is a subset of U2 intersect AB. But then, right, T minus epsilon over 2 is a smaller upper bound of U1 intersect AB, which is also a contradiction. This is very similar to the argument we made when we were doing the intermediate value theorem, right? So T can't be in U1 or U2, but that's a problem because every point in AB has to be in one of those two subsets, or one of those two sets, right? So this is impossible. Okay, so that's the proof. That's the proof that at least closed intervals AB are disconnected. So then, as a corollary, I'm restructuring this slightly from how they do it in the book. All intervals are connected. So open, closed, half open, half closed, whatever. They're all connected because for any, I, if I is, if we find U1 and U2, then there exists an A in IU1, B in IU2, then U1 and U2 disconnect AB, but we just showed this is impossible, right? So there you go. So intervals are connected, as you might expect. This actually will be useful in, well, formulating a second proof of the intermediate value theorem by first proving a generalized intermediate value theorem and then specializing that version to the case where the codomain of the function is R. So we'll look at that in the next video.